All right, as promised, we are going to talk about how to measure the correlation between two variables. This is lesson 7.5, so let's get started. We're going to take the set of data that we have, x's and y's, from the first set to the nth set of x's and y's. We're going to calculate the average of all of those x's, and we're going to call that x bar. We're going to calculate the average of the y's and call that y bar. And then we're going to plug all of that information into a formula for Pearson's correlation coefficient. It's named R, and here's how it's calculated. So we're going to subtract each x from x bar, we're going to subtract each y from y bar, multiply those together and add it all up. That goes in the numerator. In the denominator, we're going to square those differences, add them up, and then multiply them, then take the square root. Now, the reason that I'm going through this so fast is because it's nice to know what that formula is, just so you know what your calculator is doing, but you don't need to know what this formula is. It's just kind of nice to know, have some knowledge of where that number comes from. Our calculator even calculates it for us, but let's talk about what those values can be for R and what they tell us. So the very lowest value that R can take on is -1, and if it does take on a value of -1, we call that a perfect negative correlation, meaning that all of the dots line up perfectly on a line that has a negative slope. All right. Now, if your R value is a little bit bigger than 1, or a little bit bigger than -1, and somewhere between that and -0.95, we call that a very strong negative correlation. Because it's still a negative number, it's a negative correlation. If it's between just after -0.95 and -0.87, that's a strong negative correlation, but not very strong. If it's between just after -0.87 and -0.5, that's a moderate negative correlation. If it's between just after -0.5 and -0.1, that's a weak negative because we're still in the negative R values here. Now, once we're in the middle between -0.1 and +0.1, not including those values, there's no correlation at all. And then once we get into the positives, we use the same adjectives, except we use positive instead of negative because now my R values are positive. So if it's between 0.1 and 0.5, it's a weak positive correlation. If it's between 0.5 and 0.87, it's a moderate positive correlation. If it's between 0.87 and 0.9, a strong positive correlation. Between 0.95 and not quite 1, it's a very strong positive correlation. And lastly, if it equals 1, it's a perfect positive correlation, meaning that the dots line up perfectly on a line that has positive slope. So those are all the values that R can take on. How do I find this on a calculator? Well, first I take all of my x's and y's and I put them in a calculator in the statistics editor, making 2 columns. I plot the scatter plot just so that I can see what those dots look like. And then I calculate a linear regression. There is a linear regression. It's different on each calculator. If you don't know how to do that, I can show you. Also, you need to make sure that your diagnostics are turned on so that you see the values of R and R squared. If you don't know how to do that, I can show you that as well. But if you look at this, you see that in each case, A takes on a value of -0.9666 repeating. And that means that the slope is going to be that amount, -0.966. B represents the y-intercept, so that's going to be about 10.8333 repeating. But then just after that, you see R and R squared. And R in this case takes on a value of -0.8589058. So that's a negative value. I know it's a negative correlation. It turns out to be a moderate negative correlation. All right, so you see the R squared that showed up in those results as well. That's called the coefficient of determination. So it's also listed in there with the results. We saw it. If there's a causal relationship between the two variables, then R squared is going to tell us the percentage of variation in the dependent variable that can be explained by the variation in the independent variable. So a lot of words, but let's use an example to kind of explain what that means. So there's a father's height and a son's height over time. And so using the same process, I plug it into the calculator, I do a scatter plot, I do a linear regression, and I get that R squared is 0.683236. Now, what does that mean? It means that 68.3% of the variation in the son's height can be explained by the variation in the father's height. So just get used to that terminology just in case you're asked a question about this. If you have any questions, please let me know, and I will see you tomorrow.